In C#, both a double and a decimal will hold what appears to be the same value. But these are two very different variable types. So let's understand why to use one over the other, as well as how both get stored. Now, videos like these are paid for by people who purchase training at IamTimCorey.com. If you're looking to improve your development skills, keep up with AI, or even just learn to have fun building games, head over to IamTimCorey.com and check it out. And if you want the source code from today's video, click the link in the description. Finally, if you want to see something specific covered either here or in a paid course, head over to the newly revamped suggestion sites at suggestions.iamtimcorey.com to vote on upcoming topics. Okay, so I already have the code written for this video, and there's a lot here. Okay, so we're gonna go through a lot, and a lot of this is just showing you what's happening. Okay, so a lot here. I'll give you the source code again. That's linked down in the description. But I want to run through this and talk about double versus decimal. And here's the basic example that everyone sees and freaks out about. So the basic example is 0.1 plus 0.2. If we're in double, we get 0.30000 for a number of them, and then 4. But in decimal, we get 0.1 plus 0.2 equals 0.3, which is precisely what we're expecting. Now, you may look at this and go, well, 0.1 plus 0.2, why isn't that just 0.3? Why does it have all this extra stuff? We're going to understand that in this video and understand why, even though you get a little bit of imprecision here, we still want to use double almost all the time when we need a number that has a decimal point in it. So let's start off with understanding how a decimal is stored. This is the decimal type. Now, this is going to get a bit technical, but think of this like the computer science education you kind of missed maybe. So a decimal is stored in 128 bits. 96 bits, okay, right here, 96 bits represent an integer. An integer is a whole number. 1 bit represents the sign. Now, a sign is either positive or negative. And then 8 scale bits. So this is the scale. We're going to see that in just a minute. And the scale is from 0 to 28. This is how to move the decimal point around. And then finally, there is 16 reserved bits. So all of this adds up together to be our 128 bits. So I think actually I'm missing a couple of bits here. It's more than 16 bits. There's some extra. 16 plus all the rest. Okay, there's actually 2 different places of reservation. So in any event, let's figure out how this is actually stored on disk. Because remember, when a computer stores data, it stores it in bits. And what are bits? Bits are ones and zeros. So we have, 1, 1, 0, 1, like that's 4 bits, okay? So let's see how we're storing a decimal number on the hard drive or in memory, actually. So if we're going to store 123.45 as a decimal, you would store 12345. Okay, that's the integer we're storing. Now notice we just dropped the decimal entirely. Now we also store the sign, again, positive or negative. We store 0 for positive, meaning there's no minus sign here. And that goes in the flags area. Also in the flags area, we store a scale of 2. What does 2 mean? Well, notice that the decimal point here, we moved it 1, 2 places and then put it right here. So you move it 2, therefore the scale is 2. So now this results in 1, 2, 3, 4, 5. This is the formula to get back to the number. 1, 2, 3, 4, 5 times 10 to the power of negative 2. Okay, so this is the scale right here. So right there is the scale. That's at 2. We just put a negative in front of it. And then we have no negative sign up front because this was a positive, therefore we don't do anything. And we have our integer here. So 1, 2, 3, 4, 5, or 12,345 times 10 to the negative second power. That results in 123.45. Okay, so here's another example. Negative 123.45. Well, it's all the same, pretty much. It's 1, 2, 3, 4, 5 is stored as an integer. The scale is still 2. These are still moving that decimal point 2 to the right. And the sign is what changed. It's a 1. So now it's negative 1, 2, 3, 4, 5 times 10 to the power of negative 2. So notice here, this sign right here is not about this sign. They're two different signs, okay? The one on the right, the power, that's based upon how many decimal points you move to the right. Okay, so let's do one more. So we have 0.1 as a decimal. Well, we're storing 1 in the value position. We're storing 0 because of the positive in the sign position, and the scale is 1. Why? Because we moved this decimal 1 to the right. So 1 times 10 to the negative 1. Okay? And so you might be saying, man, Tim, this is a lot of math here. Why are we doing all of this? I want you to understand how it's stored. Okay? Now, you don't have to remember all this. Again, you got the source code if you want it, but I want to at least get you an understanding of how this works. Because now, let's talk about double. Double is stored differently. We're storing 1 sign bit. So that's, again, positive or negative. 0 being positive, 1 being negative. 11 exponent bits, and 52 significans that are bits, okay? This is the fraction. Now, what does this really mean? Let's look at an example because it's getting a bit more complicated, but I will tell you this is faster. Okay, so we're trying to double now, which does have that rounding error. We're going to see why. So let's look at a binary representation of 0.1. So binary, the representation of 0.1 is this number right here. So 0 point, and I've got 0001, 1001, 1001, and we got this repeating pattern here. Why? Well, remember that we're storing in binary. Binary is ones and zeros. Well, how do you store 0.1, which is a fraction? And that fraction isn't easily divisible between a 1 and a 0. It's kind of like in base 10, or how we normally think of numbers. If we were to try and calculate what is 1 divided by 3. Well, that equals 0.3333 repeating, right? Like we can never stop saying 3. And eventually we say, well, either we say 4, which isn't quite right because we're rounding up from a 3, or we just end it right here. But our division just kind of, or our division ends up at this repeating number. So we have this repeating pattern as well in our 0.1. We got this 1001, 1001, 1001. It just keeps going. Now I've put spaces in here to try and make this a little easier to read, but obviously a binary doesn't actually have spaces. So to store a 0.1 as a double, you would get a sign of 0 because it's positive. We get 10119 stored in the exponent area. Okay, because what we're actually looking for is, and let's look at this count here. We need to move this decimal point till it's 1 after the 1. Okay, so we're gonna put it right here, which means we have to move it 1, 2, 3, 4 positions to the right, which means -4. We take that -4, we add 1023. You may say that's an arbitrary number. Well, yes and no. What that number represents is the very middle of the overall binary value for a double. So it's right in the middle. So what that means is we have 0 to 123, 123 to whatever the value is in the top. But that puts it in the middle. That way it can figure out positives and negatives for the sign for the exponent. Now, why we have a sign of the exponent, we also have a sign up here, because we need to know, are we moving to the right or to the left? Because a decimal point could be, we have to move to the left. We're going to see that in a minute. But for right now, we're moving -4. So -4 plus 123 gives us 119. Now, we need to calculate the fraction. So the fraction is everything after this dividing line. We put the decimal point here. So everything after this, we need to have 52 places we're going to capture, which let's do some counting here. So we got 4 plus 8 is 12. Then we have 20. Check our math here. 28, then 36, then 44. Then we have 52. So we end right here. Okay, so all of this from this left mark to this right mark, all of that is the fraction that we're going to store. But again, this is a repeating number. So what do you do when you have a repeating number? You look at the position right after the repetition, or right after you're done, and say, okay, we have a 1 here. Remember, it's ones and zeros is all there is. So do we need to round? Well, yes, we do, because this is a 1. So we add 1 to this spot right here, which gives us 0, carry the 1, and 1. So that last 4 numbers is 1010 instead of 1001 because of the round. So that's this right here. So this whole thing is the fraction. That results in this number, 1.1, I'm not going to read the whole thing, times 2, binary, to the power of -4, okay? So again, the reason why it says -4 here is because it did the calculation backwards. We stored 1019. It knows that 1023 is the middle point, and says, okay, 1019 minus 1013 is -4, therefore that's our exponent. So 2 to the power of -4 times this number right here, that gives us, in theory, 0.1, but it's not quite 0.1 because of this rounding right here, okay? We rounded here, we ended up with the 10 instead of 01. That's where we get a little bit of the round at that last place, okay? So that's how we store 0.1. Let's do -0.1. Well, it's just a sign. That's really the only thing that changes. So when we look at the storage here, we see the sign is 1 because it's negative, but we still have the -4. So still the 1019. We still have the same fraction. So we still get the times 2 to the -4 power, but our number here, we start with a -1 or negative in the beginning. I also want to point out, we're starting with a 1 here, but that's not actually stored in the actual double. Like we have the sign of 01, we have the 1019 for the exponent, and we have the fraction, but the fraction doesn't contain this first 1. This is actually a bonus value we get because we got to assume that since we moved this decimal point over until it's right here, after the first 1, we can assume this 1 exists. So therefore, we can add this as actually the 53rd bit. Okay, so it's kind of a bonus value there, just a little bit of extra. Okay, so that's how you represent -0.1 in binary for double. Okay, let's look at one more. Let's look at 123.45. Well, first of all, we have numbers to the left of the decimal point. So guess what? We need to count how many. 1, 2, 3, 4, 5, 6. We're going to put the decimal point right there. So therefore, we put 6 here and add it to 1023 and get 1029. Again, we're a positive, so 0. And then the remaining actually starts from our decimal. So it starts right here and it goes this direction. Okay, so we're not going to go through the whole thing here, but that's our one dot. Again, that one is a bonus, and we have our remainder. We multiply that by 2 to the 6th power, and that gives us back our number, or close to our number, for that double value. Okay, so this is how decimal versus double stores the information in binary. Again, computers work with binary, ones and zeros, in their memory. So when you're talking about storing information, you're not storing the actual decimal number. You're not storing this. What you're storing is well, like this. It's actually like this data right here, which represents this. So it's a little different. So that's why when we're storing decimal numbers, it's kind of hard because binary doesn't just, put a dot. You got to convert from base 10 to base 2, and that causes some fractional issues. And they do things differently because decimal actually stores an integer on the hard drive and then moves the decimal point around, whereas double actually tries to store a value that represents the decimal number, the number that has a decimal point, which is a double. But because of that, we have some rounding differences in doubles. Okay, so let's also talk about size differences. A double takes up 8 bytes. Remember, one byte is 8 bits. So 64 bits go into a double, whereas 128 bits go into a decimal. It takes up twice the size to store the information about a decimal. So if we had 10 million values, we'd have doubles would take up 76 megabytes, whereas decimals would take up 153 megabytes. Now, do you have 10 million variables for doubles versus decimals? Maybe, but either way, it just shows the size difference. Yes, this is tiny when you're talking about 1 or 2, but there are other reasons why we should think about double versus decimal differently. So let's talk about the speed. So a double, and I should have labeled this better, but the double takes 23 milliseconds to do calculations on that 10 million doubles, versus decimal, same 10 million numbers, but does calculations on it as a decimal. It takes 210 milliseconds, almost an order of magnitude different in terms of speed. Okay. Then we're talking about the overall benefits. So the overall benefits of a double comes down to speed. They're a lot faster. They take up less memory size. They have a massive range compared to decimal. So the amount of space inside of a double is so much larger than decimal. And then finally, CPUs, almost every CPU has floating point optimization or floating point processing in there that allows for some significant speed advantages for processing things like add, subtract, divide, multiply with doubles compared to decimals. So doubles are faster, doubles are smaller, doubles have a larger range. So why do we even have decimals? Precision. So one way to talk about this is if you're talking about money, you want to be very precise, right? You don't want your bank account to have money drift out of it over time. You want to be very precise. So when you're talking about things like how fast did my car go? Well, you're measuring that, but are you super precise? Are you precise down to the 10,000th decimal point? No, you're saying it went 60 miles an hour. Well, that's a rounding issue, actually. Well, for those kind of things, double works just fine, which also is why you find double in so many games. Because if we're talking about, what angle to go at, use double. Because yes, it's not exact, but it's really close. And that's good enough because of the fact we have CPU optimization, the smaller memory size, the faster processing. So what are the drawbacks? Well, for double, you get some rounding. Again, at the very beginning, we saw that simple example where 0.1 plus 0.2 equals 0.300000004. Okay, because there was a little bit of rounding. But we give up a little bit of precision for the speed, memory size, and massive range and the optimizations. What are the drawbacks of decimal? Well, they're slower. They take up more memory, and there's a smaller range of numbers inside of a decimal. So when you're talking about decimals, when it comes to processing, again, there's CPU optimization for doubles. There's not for decimals. So the CPU is doing multiple steps of manual processing to figure out a decimal and figure out the operations for a decimal versus possibly even one step for a double. Okay, so when to use? For doubles, almost all calculations. If you're using calculation, if you're trying to measure something, you're almost always using double. Again, think about this. When you're measuring speed, it's miles per hour. We're not talking about super fractional things. And even if you had fractions of, 60.356521, that can still fit in a double, and the rounding issues will be barely noticeable. Again, it's that last bit that may or may not be rounded. And then, if we're talking about the temperature, or we're talking about, the distance that you went, all these things are calculations that you're never going to be exactly precise. Okay. And then decimal, you'd want to use that for money and other counted items that need precision. So if you're counting things specifically, again, money is a great example because we have dollars and cents. Okay. If you're in the US, it's dollars and cents. We have, 100 cents equals $1. And so you say, I have $23.15. You don't want that to be $23.15.00001. You want it to be 15 cents. Okay. So that's where those counted things need that precision. Okay. So that's double versus decimal. These conclusions are ones you've probably heard before. Use decimal for money and double for almost everything else. But now you know why. Because it's not just because Tim told me to, or because I was told that in a textbook. Now you know how it's stored on disk and why specifically you should choose one over the other. So there's a source code for it. Again, if you want to go into more depth and understand a bit more about why it's doing what it's doing, you can look at this, you can read the results, you can try it out for yourself, use different numbers. I did create some things like down here we have quick benchmark it takes a row count of 10,000. What you can do is 10 million. You can change that to 20 million, see what happens. Up here we have representing the binary representation of a number. Well, I just pass that number in. So you can change that and see what happens and look at it and actually count out to figure out how the number would be then stored on disk. Okay. So all of this you can play around with. There's the methods down below. This is all just in one program.cs, but this is now a much better understanding for you of double versus decimal. You may ask, what about float? Well, float is just double, but smaller. Okay. I think float is 32-bit versus double is 64-bit. Okay. Long is 128-bit. So it's just about how much storage space you have for that integer or that number. Okay. So that's the only real difference when it comes to float, double, and long. Okay. So decimal is for the precision. Almost everything else use double. If you have the math library, if you use the math library from Microsoft for doing calculations, it's doubles because that's the thing we have the most speed on it. They're much, much faster to use. Okay. Thanks for watching. And as always, I am Tim Corey.